Welcome to this explainer. Okay, today we're going to completely demystify the initial hurdles of learning to code. Because let's be honest, looking at a blank screen can be incredibly intimidating. But think about it this way. Writing software is exactly like constructing a building. You don't just start throwing bricks around, right? You need a solid foundation, you need the right tools, and you absolutely need a clear blueprint. We're going to treat your first steps in programming exactly like that, starting right from the ground up. And the best part? Whether you are using Python, Java, or Visual Basic, the core architectural principles remain exactly the same. It's like learning to drive. Once you know the rules of the road, you can drive almost any car. So let's dive right into this. Here is our blueprint for today. 1. Choosing your tool. 2. Writing your first program. 3. Core programming concepts. 4. From pseudocode to code. And finally, 5. Testing and trace tables. Section 1. Choosing your programming tool. Before we can build absolutely anything, we have to gather our tools. In the programming world, this means selecting an integrated development environment, which you'll almost always hear called an IDE. This is basically your digital workbench. Now, you might use Python's clean, free, idle environment. Fun fact about that, it's actually named after Monty Python's Eric Idle. Or you might use Visual Studio's Community Edition, which is super common if you're writing Visual Basic. Now, Visual Studio might look a little bit like an aircraft dashboard with its Solution Explorer and all those properties panels, but please don't let the interface intimidate you. Underneath it all, these IDEs serve the exact same purpose. They simply give you a place to write your text, compile it, and actually see the results. They are just different brands of hammers for our construction project. Alternatively, maybe your syllabus or your school relies heavily on Java. If so, you'll likely use the free BlueJ environment. BlueJ is actually fantastic for beginners because it provides a highly visual project window. Instead of just staring at lines of text, you literally construct visual blocks called classes before you even write a single line of code. It really helps you see the structure. You'd set up a class, maybe name it Hello World, double-click that icon, and then get to work in the editor. But look, whatever language you choose, getting this environment installed and running is your crucial first step. Section 2. Writing your first program. All right, now let's prove our tools actually work by laying our very first brick. We are going to write the absolute classic foundational program, Hello World. Creating this program usually boils down to 4 straightforward structural steps, no matter what IDE you're in. First, you create a new file. Second, you type your command. In Python, for instance, that's just typing the word print followed by hello world in parentheses and quotes. Third, you save your work, always save your work, and finally, you run it. In many IDEs, just hitting the F5 key on your keyboard will compile and execute your logic in console mode, and you'll see that beautiful hello world text pop out on your screen. It's a small step, but it is a real milestone. But wait, what if it doesn't work? What if you hit F5 and a big red error pops up? The most crucial thing to remember here is do not panic. If you see an error like EOL, which simply stands for end of line, you probably just forgot a closing quotation mark. It's no big deal. Think about it. When you are building a physical structure, you might occasionally hit your thumb with a hammer. In programming, you'll misspell a command or forget a bracket. Syntax errors are a completely normal, everyday part of the process. In fact, here's a great piece of trivia. The first computer bug was an actual, literal moth trapped in a physical relay switch back in 1947. Your IDE isn't yelling at you, it is simply tapping you on the shoulder to help you find a simple typo before the program runs. Section 3. Core Programming Concepts. Okay, with our environment proven and our first program officially running, we need to frame the structure of our code. Let's look at the actual load-bearing pillars of programming required by your computer science syllabus. The first, and arguably most important concept, is sequence. Sequence is absolutely crucial because a computer is highly, relentlessly literal. It will execute your instructions exactly in the order you provide them, strictly top to bottom. If you tell a program to input 3 numbers, calculate the total, and then print the result, it must happen exactly in that order. You literally can't ask it to print the total before the numbers have even been inputted. It sounds obvious, but getting your sequence out of order is a super common trap. Next up is selection. Think of this as a fork in the road of your blueprint. You don't always want your program to do the exact same thing every single time it runs, right? Selection uses IF statements to make dynamic decisions. For example, a user inputs a negative number, then show an error message, else proceed with the calculation. It makes your code smart. You can even use logical operators like and or to create highly specific, nested conditions to decide exactly which block of code should run next. Our third pillar is iteration. Iteration is simply a loop, and this is where computers really show off their power. Imagine having to write the exact same line of code 1,000 times to process 1,000 different student records. That would be an absolute nightmare. Iteration acts like running laps around a track. We utilize structures like a repeat until loop to keep asking a user for a password until they get it right, or we use nested for next loops to efficiently output the numbers 1 to 10 20 times over. It essentially automates all the repetitive heavy lifting so you don't have to. Now, beyond those three structures, a master builder has to know how to handle their materials. In programming, that material is data. You need to identify basic data types, like using integers for whole numbers or strings for text. You'll need to set up variables to count how many times your loops have run. And crucially, you need to know how to manipulate text strings. Examiners love testing this. The syllabus specifically wants you to know how to find the exact length of a string, how to convert it entirely to uppercase or lowercase, and how to isolate just the very first character. Think of these as your fine finishing tools. Section 4, From Pseudocode to Toad. Let's put this all into practice and test our understanding of sequence and data handling. We're going to look at an algorithm that needs some serious fixing. Now, pseudocode is basically a rough sketch of a program written in plain, easily readable English. But what happens if the sketch is a mess? Imagine a jumbled algorithm designed to input 10 positive numbers, total them up, and output the mathematical average. But the steps are entirely out of order. Variables are being added together before they're even declared, and outputs are happening before inputs. Your job as a programmer is to untangle this into a logical sequence. You'd need to first declare your integer and real variables, and remember, real variables simply mean numbers with decimals. Then you set your starting counts to 0, initiate your loops, ask for the inputs, ensure those inputs are actually greater than 0, add them up, and only at the very end calculate the average and output it. Fixing this kind of disorder is just a fantastic exercise in logical, step-by-step thinking. Section 5, Testing and Trace Tables. Let's move to our final section. The final step of any physical build is the inspection phase. I mean, you wouldn't open a newly constructed bridge without rigorously testing its weight limit, right? In programming, this means strictly testing our code against expected outcomes. Imagine we've built a program for a parcel delivery service. The rules are super strict. The program must only accept parcel weights between 0.5 and 5.0 kilograms. Any lighter or any heavier, and it should immediately reject it. It then displays a menu of 5 specific delivery options, ranging from guaranteed next day to standard 3 to 5 day delivery, and finally calculates the cost. The big question is, how do we definitively prove to an examiner or an eventual client that this logic actually works flawlessly? Well, we use what's called a trace table. We meticulously push specific test data through our logic just to see if it breaks. We don't just test normal, easy numbers. We intentionally test the extreme boundaries. For instance, we enter 0.4 kilograms, which should definitely trigger an error. We test 5.1 kilograms, another expected error. We even throw in a completely invalid -1 just to see what happens. Then we test the exact boundary, 0.5 kilograms alongside option 1 to make absolutely sure the calculation fires correctly. By documenting the expected output against the actual output, we definitively prove our logic handles both standard expected inputs and weird edge case errors perfectly. And there you have it. You now possess the complete builder's blueprint. We've walked through selecting our IDE, getting that first exciting hello world onto the screen, understanding the foundational pillars of sequence, selection, and iteration, untangling messy pseudocode, and finally, effectively testing your code with trace tables. So I leave you with this question. Now that you understand how these digital bricks are laid, what real-world problem are you inspired to solve first? Thank you so much for joining me on this explainer, and happy building!